Okay, so now we got to the hard part. If I can mangle a famous comment and say now we've got down to the psychologists. There's two of them left. And the first one, I guess, would be generous. We could even call Tor a statistician, at least in some universe. So Tor is going to give us, I guess, a number of things, but some meta-analysis in particular. Okay.
Well, I'm not sure which universe it is exactly, but I'm glad to be there. The dark universe. And I hope that you finish this talk and most of you will continue to do exactly what you were doing before, at least with meta-analysis. I'm going to talk a little bit about, let's talk about meta-analysis and some pitfalls and some emerging solutions. And I just wanted to start with a motivator for why we do meta-analysis and the fact that it's important. It's good to remind ourselves of this. So first of all, PET and fMRI studies are obviously growing at a very rapid rate. They're the most popular techniques out there right now for a variety of reasons, in part because people can really use them across different fields, which is wonderful. But this gives us thousands and thousands of studies to integrate. And this also creates a lot of problems, and there's a lot of debates about the degree to which our findings are really useful for the broader world. And this is a very disturbing sort of headline from a New Scientist cover. Yingfei Chen writes, "The vast majority of brain research is now drowning in uncertainty." And a lot of this has been a response to various crises that have sort of come up in science, but also really in the popular media, including the crisis of small sample sizes and reliability, a crisis of replicability and effect size estimates. This extends beyond brain imaging to think about gene-environment interactions, or maybe just all studies on average. So I think that meta-analysis is in part a solution to many of these problems, which is why I started doing it years ago. So to remind us, I think one of the goals of meta-analysis is to build a cumulative science. So there are many findings out there in the literature, and what we need to do is to integrate the most reliable of those to build a cumulative science. And quantitative summaries can help do that by turning a bunch of coordinates from published studies, like the ones you see here related to emotion, into, for starters, a consensus map of areas that are activated reliably across tasks and conditions. And this is one way of summarizing meta-analyses. Since I created this slide, there are more. I didn't update it. Now there's probably 360 meta-analyses out there across all kinds of different clinical and basic topics. And this is another list if you prefer this format. But instead of trying to read this, this table is from this paper cited below, which I think is useful and has some pointers to what's out there. So I think there are three things that we need that meta-analysis can help us provide. And one is measures of consistency, so establishing replicability in precise a priori regions or patterns of interest that we can use in a variety of ways in our individual studies. The second one is sensitivity. So it can help improve, it can help essentially borrow strength from prior studies to help increase measures of effect size and provide unbiased measures of effect size. So if you get to test the anterior cingulate cortex for an effect, or the amygdala, and you can choose any one of hundreds or thousands of voxels in the amygdala to test, then you're going to get an answer, a positive finding in many studies, in many different conditions, but they won't all be true. And so if we can really home in on what our prior expectations really are, that's going to be helpful. And the third is specificity. So our ability to assess what activation patterns mean psychologically and functionally. And this is going to require integrating information across many different studies and many different tasks and many different conditions. Of course, meta-analysis has its own pitfalls, which are, I'm going to talk about a few of those today. I'm sure I've missed some. So I've talked about why meta-analysis, and I'm going to talk about several things. Briefly, the idea of what do you want your meta-analysis to tell you, or what kinds of inferences are we making. I'll talk about a few pitfalls and some solutions, and I'll talk briefly about some new kinds of inferences that we can make and how those might be valuable. And then finally, all good meals should end with pudding. So I'm going to talk about this one idea that the proof is in the pudding for what meta-analysis can do for us. So we should start any endeavor or study by thinking about what we'd like to conclude from our analysis. And the most common type of inference that people make, and this is most of the studies, or virtually all the meta-analyses out there, is about the activation consistency. So we're saying take a task X, maybe it's working memory task, and we're asking, is there consistent activation across these different studies or paradigms? We can also ask, similarly, are there overlapping brain regions for two tasks, X and Y? Maybe it's working memory and spatial attention. Are there significant differences in activation consistency as well? So these all fall in the same family. And I'll just give you a concrete example. So this is from a series of meta-analysis that we did several years ago. There's a meta-analysis of consistent activations in working memory, executive working memory, long-term memory. Now we can start to identify the regions that are commonly activated across all of them. Here's inhibition, which is cognitive inhibition and response selection, task switching, what's common to those. And we can start to make maps of the overlap. If we care about the sort of epicenter of everything, it turns out the inferior frontal junction is a pretty good one in this case, and where the sort of specificity might lie. So that's just an example. However, this is pitfall number one, I think. This type of inference doesn't really tell us a lot of the things that we want to know. It seems very familiar if you've ever done a meta-analysis, but consider other types of inference that we might want to make, and if we're a little bit creative, we can come up with measures of these things. So one is spatial inference. If I'm actually asking where is the epicenter of activation for task X, my meta-analysis is not showing you that. It's not. Do tasks X and Y activate the same locations or the same spatial patterns? And you can apply this to individual studies too, as well as meta-analyses. But this is different from asking whether I get consistent result at each voxel, because it's really about where. And maybe we actually want to know about where. A second type of inference is decoding or reverse inference. What type of psychological process or category of processes is implied by activation of a region or a pattern? And then what I'll call representational inference, which is this idea of understanding what brain features or patterns are required to make a prediction about task X versus Y. So what's the basis that I need? I'll talk a little bit more about that actually tomorrow in a morning workshop. Not about meta-analysis, but with regard to an individual study. So that's a little bit about types of inferences. If you don't believe me about spatial inference, I'll kind of unpack that a little bit as I go along. So here's pitfall number one. It's really about the failure to assess generalization across studies. This is already something that it's sort of more or less fixed for many of us with newer approaches, but I think it's worth saying it. We typically analyze peak coordinates. If you're going to take a naive approach to meta-analysis, you might lump all the peaks together and then look at where there's consistent peak reports across studies. And the problem with this is that you're not taking into account the study as a level of analysis. And so the results that you get can be dominated by some studies that report more peaks, for example. So this is the idea of how this would work, right? And it's worked in sort of early versions of software. You take a number of reported coordinates from literature, combine them into a map of peaks. Typically there's a kernel, a convolution. So basically each of those points is smoothed in space. And then you end up with a map. And then you do a Monte Carlo test by shuffling the peak locations around in the brain and then coming up with a estimate of what the null hypothesis should look like, and then you end up with some significant results. So the problem with this is that these peaks are not uniformly reported across studies. So you can see there's 3 example studies here. These are actually real studies from the literature. Top one is Damasio et al. 2001, I believe, Nature Neuroscience, if I remember that right. So they report lots of peaks. It's pretty much arbitrary how many peaks people report. And then the other study reports only 2 peaks, and then fewer, right? So if you just lump them all together, really you're just going to potentially get out a representation of the studies that reported the most peaks. Okay. So this is an update to that, and we can solve that problem fairly easily by considering the multi-level nature of the data. And so you might take the reported coordinates in literature, but separate them out per study or per contrast, and convolve those, and then you end up with a reconstructed contrast map for every study or every individual contrast you're putting in. And then you can calculate a weighted average across those, and then threshold with a Monte Carlo procedure, and then you get a map. And what this does, and there's several sort of tricks to this, but what this does is it gives us an estimate in our weighted average map of how many studies activated in a local region, not how many peaks there were. And that's the key. That's what we'd like to know. So in our software implementation, we use a spherical convolution so that we get something like counts, numbers of studies that activate in a local region, because that's interpretable. We weight by the square root of the sample size, and we weight by whether something is fixed or random effects analysis, and there's other quality metrics that you can apply. And I'll talk a little bit more about that. And that leads us to pitfall number 2, which is there are lots of ways of accounting for biases, like different numbers of studies report different numbers of coordinates, different studies report different effect sizes, different studies use different analyses. And so I call this pitfall improper accounting for biases. So studies vary a lot in sample size and other things. And I also wanted to make this point that, in SPM or in FSL, there's no really principled way of deciding if you have this sort of big blob of activation, how many coordinates you're going to report, how far apart are they, how do you determine what the local peaks are. Those are pretty much arbitrary choices. They're not really principled. We're not making inferences on them. So the data I'm putting into my meta-analysis are, the result of some arbitrary processes. And here are some potential solutions. You could forget about all that stuff and not do anything to weight them, and that's not very efficient. It's low power. In any meta-analysis, if you look at the literature, you really want the large studies to dominate. You don't want to weight a study equally with 900 people and with 30 people, and say, oh, I got one of each, right? Weighting by the square root of the sample size is good. Because essentially then that weights it in proportion to the standard error or its precision. And weighting by random versus fixed effects is a good idea. Random effect studies should have more weight, but there's no theoretically optimal weight, so that's an unsolved problem that you could address and solve if you're smarter than me and can figure that out. But certainly we should upweight random effects studies and other studies that have essentially higher indicators of quality by whatever you think quality is. And weighting by z-scores is probably a bad idea. So I wanted to say this because I think it's being done a fair amount in the literature. So why is it a bad idea? Well, let's talk a little bit more about this. And I'll just introduce an idea here that is I think standard in the meta-analysis literature in many circles, but I think it hasn't made its way into neuroimaging yet very much. And this is called a Galbraith plot, but I've modified it. And what it is, it's a plot of the square root of the sample size against the z-score, which is the estimate of the effect size from a given study. And this is real data from a meta-analysis of working memory that we published some years ago. So that's all real. And the idea, if you look at my little A plots up there, is one thing it can do is help detect a bias in publication bias, reporting bias. And the way it works is if there's no bias, then the intercept of this relationship between sample size and z-score should fall along should go through the intercept, which is the diamond, right? So if the sample size is 0, you shouldn't see an effect. That's what it's saying. However, if there is a small sample reporting bias, then you'll have an intercept, right? And so this plot, it's sort of interesting. What you can see is for the fixed effects analyses in the working memory database, it goes through the intercept. There's not really a bias. For the random effects analyses, there is a bias. There's a publication bias. Does that mean random effects analyses are worse? No, it doesn't. What it means is that they're underpowered. And so people do random effects analyses, they don't find anything, but they know they need to do the analysis, and so they report something that they have, right? So the intercept's not 0. What it really means is we need bigger studies. But if you notice, first of all, if we weighted by z-scores are much higher for fixed effects analyses. And then here's another interesting phenomenon, or there's if you look at the random effect studies especially, there's a very weak relationship between the sample size and z-score. So we know bigger studies are better, right? But our higher z-score is better. Should we upweight those, in a meta-analysis? Not necessarily. And here's, I think, why. So small studies have higher variance, right? It's very hard to get precise estimates of the standard errors in these studies with small sample size. So their maps are really rough. That means that there's a lot of stuff happening by chance. And what that means is there's a lot of points that have high z-scores by chance. So when you pick the winners, they tend to have really high z-scores. So basically, that means more peaks overall, and especially more peaks in false positive regions for small studies. So all that amounts to this idea that I think weighting by z-scores, or even the number of peaks that people report, which is possible too, is a bad idea. So one thing that we do that helps to deal with that in our approach is if we permute the peaks within the studies too, then again those small studies are going to end up dominating and having lots of peaks, and then the bar for what counts as null hypothesis values in your Monte Carlo test goes up. And those that report many coordinates will dominate. And so we can address those problems by, instead of permuting the peaks, we take study by study and take the contiguous regions of activation, our blobs for each individual studies, and we move around the locations of those. So that helps guard against that kind of bias and produces more sensitive results. So all that stuff is sort of in existing software that you can use. Pitfall number 3 is erroneous spatial inference. So if we want to know where the activity is, this is an example of overlapping fMRI activity from an early study I did in 4 types of attention shifting with 40 people. So the red areas are those that are sort of, there's overlapping activation in all 4 different tasks. And the point I want to make here is that we often wonder, or I often wonder, how much overlap is enough? And people ask me this a lot. And we can either focus on the commonalities and say, these maps are really similar, or we can focus on the distinctions. So really, this is a sort of degenerate way of looking at brain maps. I think looking at the amount of overlap is not going to cut it. There's always going to be some similarities and some differences. The problem is that there's no actual spatial model for how far apart things should be or how much they should overlap. So spatial models can help provide a solution, which are very seldom used so far, but I hope they get used more often. So I can construct, like these things here are spatial confidence intervals. And so simply what you can do is take the locations within a local region for 2 or more different types of tasks, and then the X, Y, and Z coordinate locations become your data, and then you do a spatial MANOVA, and you can do a statistical test for whether these points are significantly different. So there's a number of examples in the literature, but it hasn't yet sort of made it into common practice. You can use this in meta-analysis, you can use it in individual studies as well. So I'll talk about 2 things, spatial tests and spatial models. And the first idea is spatial tests, just like I said. So you can do a spatial MANOVA test or discriminant analysis on the coordinates. Or you can do a spatial model, which is, I think, sort of more sophisticated and interesting in some ways, where you're making inferences about the distribution of coordinates. So here's an example, overlapping activity there in the right side and the top. I don't have a pointer, but it's up there in the, oh, it's here. Oh, hey. There, that little thing right there, right? In the premotor cortex. If we do a meta-analysis of different types of attention shifting, we can actually see that although there's some overlapping activation, the different types of shifting, here switching among locations and attributes and rules, are fairly differentiable. They're significantly different locations, right? So there's a lot of information there. Another interesting approach is the 3D Kolmogorov-Smirnov test, which was done some time ago. They did this to look at different emotional conditions across the whole brain, but you could also apply that to local regions and make inferences about the differences in the spatial distribution of coordinates. Now I'll talk a little bit about spatial models and end with an example. So I think this is actually really promising. So this is an example of a spatial model that Jan Kang and Tim Johnson developed at Emory a few years ago and are still using and developing. And the idea of the spatial model now is to model the generative process that generates these reported peak coordinates. So in their model, it's a 3-level model, Bayesian model, and the individual peaks that you observe, right, that get reported are drawn from activation centers for a particular study, which are latent true locations for that study, and then those in turn are drawn from a population level map. So this whole class of studies of a certain type, like working memory, produce a set of population centers, which then give rise to study specific and then observed coordinates with noise at each stage down the line. And then there's a background noise process, Poisson noise process. So this is an explicit spatial model. I won't go into the details of it, but it can provide lots of interesting things. And one of those things is a spatial test that can come out of it. So this example from this paper, where they're looking at amygdala activation for positive versus negative affect, and they find that, yes, the three-dimensional confidence regions, ellipsoids, are different for positive and negative within the amygdala, so they can observe a difference in spatial location. Talk now about reverse inference. And the idea of reverse inference is to understand, what does this map mean? Is this a typical map from a single study? And you can see the anterior cingulate activity, you can see the insula, you can see the medial thalamus, you can see S2, secondary somatosensory cortex, and the dorsal posterior insula. Your job, if you're a good cognitive neuroscientist, is to decide, what is this? What's happening here? So you should all be able to guess, right? I hope. Somatosensory, S1, okay. Take a guess, shout it out. Reverse inference is, I won't go through the details of this, but it's a formal assessment of the probability of the task type given a constrained set of alternatives. So Stephen just talked about Gaussian naive Bayes. That's this right here is what we're going to use to start with. And if you did this for a defined region, you would do something like this. If you have a defined region like S2, you can look across many different kinds of studies, and that's what we're doing here, and say, what's the probability that I'm experiencing a pain given S2? So, and these are studies of emotion and response inhibition, long-term memory. There's pain. There's shifting attention. There's working memory studies. And of course, I can broaden that out, but the upshot is that if I have activity in S2 here, the probability of this being a pain task among that set is about 87%. So that's a reverse inference. That's pretty good. So there it is. Positive predictive value of S2 activation. And these kinds of tests are implemented in various ways, but this MKDA toolbox I talked about before for us makes maps, and you can do other stuff with it too. Lots of these things with it, but you can also do, it's got a naive Bayes classifier for meta-analysis there, so you can use this and do all that relatively simply. So you can do your own naive Bayes classifiers within a region or across the brain. And that's pretty interesting and sensible. Or you can just use Neurosynth, maybe. And Neurosynth, as Tal might tell you soon, is just really, it's developed by Tal Yarkoni a few years ago. And the idea is it's a database that combines many studies and the full text of their coordinates here, the full text of the study and the coordinates. And then what you can do is search for a term like pain, and it will look at papers that talk about pain a lot, look at their coordinates, and reconstruct a meta-analytic map. I think this has been incredibly useful in many ways. It turns out there is a reverse inference button, or you can, there it is, here it is, there. You can choose reverse inference, you can get a reverse inference map, right? And as wonderful as this is, I want to sort of make a point, that this isn't really reverse inference, in the sense that I just described, where I specify the set of alternatives. What it really is, it's a one-way chi-square test for comparing whether there's an increased probability of activation versus not, if your task is, pain-related, if I put in pain versus not. So this is useful, but we have to really think about the models that we're constructing too. This is a starting place, like for many things. And there's some details of that that are not important for us now. Yep. So what does this map mean? You might have guessed already. If we put in, there's the Neurosynth, we can put in reverse inference, and we can even do some decoding, open-ended decoding, and this is what we get. Noxious heat, somatosensory, painful sensation, simulation, muscle temperature. Does that help you to guess? I hope so. But you're wrong. This is not pain. This is a romantic rejection map. Okay. So, pitfall number 4, there. Not remembering the shortcomings of what we're doing, right? Don't just use it. Understand what it's doing and when it might go wrong. I have 1 minute 20, maybe? Let me go back to at least one new tool, and this is the idea of Jan's map, right? So these are the levels of the model that I talked about, and what it does is it models that generative process, and it gives you a map. here and this will use this to apply to 5 different categories of emotion. And then from these maps, you can also derive a classification model. So we can test how well this is doing at predicting the emotion type from different studies. There's more details of this model. It's a generative Bayesian model, but that's not critical here. But it gives us a single generative model, which is a map plus co-activation across the brain, joint activation, for each of 5 emotion categories: happy, sad, fear, anger, disgust. And so you get a map, which is not the whole story, but it's part of the story. And then it turns out that you can take a new study and you can classify which of those 5 types it is, and that's the diagonal here, fairly accurately. Chances 20%, 40 to 80%. So this tells me that it's doing something that's meaningful and that we can actually differentiate the types. And the nice thing about this that's kind of cool is that we can flexibly interrogate this model, and we can carve the brain up in any way we want to, like with these resting state networks from Buckner's lab, and we can look at the profiles from each emotion across the cortex, and we can see that they're really different, and we can even break those things up into components of cortical networks and look at each emotion in the cortical networks and see. We can do some then statistical tests after the fact and say, yes, they're really different. So the profiles in the cortex are different, the profiles in the thalamus are different, et cetera. And that's the case for this data set. So the point I wanted to make here is that with this kind of generative model, we can use this very flexibly to do things that we wouldn't have thought of in the first place. And this is another example where we have a sort of graphical structure derived from the model for each of the 5 emotion categories, and we can sort of visualize then how different they are and how they might be different. So I won't give you more on that. Finally, if I can, the pudding. Back to neurosynth. What really matters is what we can do with it. I think we've come a long way in this process. I think Tal's original paper here gives us an idea about that. So we can take 3 categories: pain, emotion, working memory, and we can use neurosynth to derive this sort of posterior Gaussian Bayes classifier pattern. So those are colors associated with each of those 3. And then we can take actual maps from individual subjects, and we can put those into the classifier and ask, does the prior literature actually tell us what somebody is doing? And in this case, it was pretty nice because it's pretty accurate overall at picking out what somebody is doing with an individual person. So this is hopeful because we're using meta-analysis as a starting point then for constraining our inferences about people and building our classifier and machine learning maps. So to summarize, we talked about some uses, we talked about 4 pitfalls, and about some new models. Thanks very much.
Okay. All right, we're out of time, so we'll move on to the last speaker.